All right, thanks very much for attending today. It's really good to see all of you here. My name is Bryce Botman. I'm the Applied Innovation Manager at Shell. And I'm going to talk to you today about the latest releases of the open source versions of Apache Spark 4.0 and Delta Spark 4.0. Apache Spark 4.0 was released around 2 weeks ago, and Delta 4.0 was actually released yesterday, just in time for this. So I hope that we can use this session to talk a little bit more about all of the new features in these two versions that are going to make streaming, the ingestion and querying of streaming data better than ever before. A quick one, here's the forward-looking statement. Never quite know what to say about this slide, but anyway, we'll move on. And then on complete your surveys, just in the app at the end, if you have some time, please go in there and just fill in a survey about the presentation. So I'm suspecting that a lot of you are here today because you probably have some streaming data use cases. You may be using Spark. You may be using Delta. But how does it actually perform as a time series platform? There are a lot of options in the market in terms of what we can do with time series. But I want to try and convince you today that you can leverage Spark, the newer versions of it, as a time series lakehouse. You may be doing it already, but what I've seen in using Spark for the last 6 or 7 years is that there's been a real step change in terms of our ability to process time series data using these latest versions. And hopefully, by the end of the session, if I've been successful, you'll agree that we've got comprehensive support for time series workloads and data using Apache Spark and Delta. So there's 3 main topics that I want to talk about. And there's 3 goals that we're going to try and go through, because I think if you've tried to store streaming data, which is typically time series data, into Delta, there's been some challenges which I think have been addressed. And the first is that we need to simplify the data model. The way we define our Delta tables can often be tricky because of certain constraints. The second is we're going to talk about optimizing the data layout. So time series is often, or streaming data is often a big data ingestion problem. But the query side of it is often a needle in a haystack. You're often the user's trying to find a very specific set of data in a massive table. And so there's been some updates that really help with that. It's not particularly new to Spark 4, but I'll just go through that in a bit. And then the other one is that there's been updates around how do you actually ingest Spark data sources, streaming data sources that aren't the typical data sources that you get if you're a Python developer. We are normally familiar with ingesting streaming data from things like Kafka, Kinesis, GCP. But what if you have other ones? In all sorts of industries, there's actually a number of different protocols that you receive streaming data on. And Spark doesn't support them. So I'm going to talk a little bit about the new options that you can write your own custom data sources in Spark that makes life a lot easier. So the first one I'm going to get into is how do we simplify the data model. There is a new update called variant types that has come out in Spark 4 and Delta 4 that it makes life a lot easier. So when we look at streaming data types, the workload, the payloads that we typically see are like on the screen. This is just a simplification. I'm sure you've got far more complex ones than this. But it's typically some sort of JSON semi-structured payload. It's got some sort of identifier that tells you the device or the measurement or the reading, the timestamp that streaming data came from, or when it happened, and then your data column, like the actual values that are linked to that streaming payload. And this is where the problem often comes, in that these aren't strictly typed to a particular type. So you can have data values that can be string, that can be numeric, that can be Boolean, it can be a number of different things. And how do you cater for that type that is changing all within the same data model? And so this is where we've been talking to the Databricks and Spark communities around how do we solve this problem for a number of years now, actually. And variant types are finally the solution for it. So before Spark 4.0 and Delta 4.0, you were limited by the data types in that Spark and Delta supported. If you had numerics, you could choose things like int, floats, doubles, or decimals. You had date times, you have strings, booleans, and if you've got complex data types, you would pick something like an array, a map, or a struct. But that doesn't really help if you think about that payload that we had before, where there was an array with strings and numerics all in the same column. So how did people solve for this? If you look on the right-hand side of the slide, there are some options that we've seen people try and choose. So first one is they always kind of split out that measurement ID and the event time because they're probably going to index by it and search on the tables with it. And then they do things like, let's store that data payload in a string column that's added to the delta table. So that's the first option that you see there. The second one is people sometimes say, OK, I've got mixed types. So what I'm going to do is I'm going to create two different value columns, one that stores numerics, one that stores strings. And so you get scenarios like that, and those are often actually hard for an end user to interpret because they don't know when they should go to the string column or when they should go to the float column. And then the other one is some people try and say, OK, I'm going to decide on the exact same data schema for my table, but I'm just going to make the value column different. So I'm going to create multiple delta tables that have the exact same column names. But I'm going to create one that the value column is a string, and then one that is a decimal or a float or something along those lines to cater for the numerics. While these solve the problem, because they still maintain the strict integrity of the data types on those particular values, it's not particularly easy for end users to consume this data. They need to know which column to look at. They need to know which table to look at. And if we just put it all in a string, they also need to know how to parse that data. And at scale, parsing strings can take time. So we've had to deal with that for a while. But they've now introduced in Spark 4.0 and Delta 4.0 variant types. So these are best for semi-structured data that is common in real-time data sets like IoT telemetry, ad-click analysis, and endpoint detection and response, or any other type of payload that you get. And you simply use the command parse JSON. You can parse in the whole JSON payload into parse JSON, and what it will do is create a variant column for you in your data frame that can also be persisted into Delta as a variant column. Or you can just parse single values. So anything that is JSON related can be parsed into a variant type, and then into a variant column, and then you can query and get all of the benefits from variant types on top of that data. So now how do we use variant types? So we have the parse JSON command to actually convert JSON payloads or semi-structured payloads into a variant column. And once it's stored, we can then do a number of things on it to actually get that data out. So the first one is there is a new function called variant get. And what variant get allows you to do is basically do JSON path expressions to get the data out of that complex type. So that makes it a lot simpler. So you can kind of, just like you've done with any sort of type of TypeScript retrieval of variant of JSON payloads out of a string, you can do the same thing here. The next one is you can also cast values. So you can, because it's in a variant type, which is a byte encoding that you can see it's an open source standard, you can ask it to cast the values into a particular type. And then the last one that it can do is schema of variant, which is actually really interesting. You can run a schema of variant function on a variant column, and what it will return is actually the schema or the type of every single row in that table. So I'll talk a little bit about that in a second. But let's have a look at now, how do we architect, or how do we set up the Delta design, table design, using variant types? Well, now what we can do is we can have our same ID and event time columns that are probably driving a lot of the querying that we're doing on our tables. But we can just have one column called values, which is a variant type, and it can store anything. So in this particular table, they've decided on the first option that they're going to just store that entire payload, the data payload, as one array in variant type. And we can then get that value out using variant get, and basically we can even search in the index that is in that array. The other option, which we use, is we split those arrays out into individual rows, and we can store a numeric value in the same column as a string value, but that value 4 is respected as a numeric field, a numeric type. It's not actually converted into a string or anything. it actually behaves exactly the same as the type that we wanted it to. And the second row has got the on, which is going to be recognized as a string field. So it's by row, it actually defines what the types are for each of those values. This is really great because now it starts to simplify how do we store all of our data. We don't have to have multiple columns in tables. We don't have to have multiple delta tables. We can now have one table that can handle all of these different types. So this is a really useful feature. Now, what are the benefits? If you are today storing string payloads or your JSON payloads in a string column in Delta, you now can convert that to a variant column, get all of the benefits that I've just talked about, have all of the functionality in terms of how you pass that JSON payload and use it, but you get 8 times faster performance on reading data out of a variant column than if you had it as a JSON string. So very little reason not to use it, very powerful feature. The best thing of all is that it's open source, and Nima from Goldman Sachs also agrees that this is a great addition to the open source ecosystem. You can use this in, obviously, Databricks. You can use it in open source Spark. And that is pretty much why I wanted to include it in this, because I'm going to talk about all the open source features that make this really cool. OK, so that is variant types. So let's move on to the next topic. It's optimizing the data layout. I'm not talking about a particular feature that's come out with Spark 4.0 or Delta 4.0, but I think it's really important to talk about this one because it is a significant benefit for those that are dealing with streaming data, and it's called liquid clustering. You may have heard about them talking about this in last year's Spark Summit, or I should call it Data and AI Summit. And I'm just going to tell you a little bit more about why this really helps with streaming data. So before liquid clustering came about, the options that we had available to us as Spark developers was partitioning to improve performance on reading Delta tables. So what we would have to do in streaming data scenarios is often have to pick a column that would help us define the partitioning logic. Now, what does partitioning do? Partitioning is basically providing Spark with a few more options that helps it find the exact data set that you need in your table to read and write to. In streaming data, that partitioning column that we often choose is normally a time dimension, something like a year, a month, a day, or a date. In this particular example, the Delta table has been partitioned by date. And so what Spark does when you write to that Delta table is it actually persists each date's values under its partitioning, which is actually just a folder in the underlying table. And that then helps Spark, when you run queries like at the bottom there, when you say, I want to go and get everything where the event date is between these two dates, it'll look at the partitioning folders and actually work out exactly which files to go and read. So this provides massive performance improvements if you do not partition your tables. And if you're doing streaming data workloads, you probably have run into huge performance problems in the past. And this is one of the best levers that you can pull in terms of producing better performance. There is something else called Z ordering that was available as well as part of Delta, which also helped you, once you were in the partition, you could then navigate like which particular Parquet file. You would try and help Spark figure out exactly which Parquet file to read. But that worked, and it's actually still very successful, and I'm sure a lot of you have partitioned Delta tables today. But liquid clustering has tried to alleviate us with some of the challenges with partitioning. Ali Ghodsi always says, I'm sure he's going to say it tomorrow, that they're going to try and figure out how to reduce the amount of dials and switches you have to use to get Spark to work as best as possible. And liquid clustering is one of the steps towards that. So liquid clustering is basically the Z ordering that you're probably familiar with on steroids. If those of you who don't know what I'm talking about at all, if you think about an index and a database table, clustering and liquid clustering provides very similar capability. You will create a Delta table and say, I want to cluster by certain columns. And what then happens is the data is arranged in your Delta table where it clusters on those columns and puts the data together in as close as possible Parquet files in your Delta table, so that when Spark has to go and look and find the data in that table, it has to read a lot less files than before. So it's a combination. So when you trigger a query and it goes to the query engine, it's a combination of looking at the delta log to find out which Parquet files it should actually read in the underlying delta table, but it also uses statistics, which helps it really narrow down the exact type of Parquet file to retrieve, or which of the Parquet files it should retrieve. So again, we're going to run a similar query on it, and I want to show you the performance improvements. So I've created here a table that has 2.5 terabytes of streaming data in it. There's about 200,000 different devices that are in this table. We are using Databricks SQL, extra small cluster. I'm trying to think of everything that I use so that you can see that it was all equally tested. The one is on the partition table, and the other one is on the liquid clustered table. Now, if we look at the partition table on the left-hand side, you'll see that the partitioning did a really good job. When it took the 2.5 terabyte table and we ran this query, it filtered down using the partitioning logic to only reading 30 gigabytes of data. But the files it read were 370. The query that I ran was for a year of data. So the 370 kind of correlates to how many partitions are actually in that table. And that's still a good job, right? That is still a lot better than what we would expect if we ran it on a full scan on the table. But now let's have a look at liquid clustered tables. In liquid clustered table, it was able to narrow down the amount of data it needed to go and read to just 6.94 gigabytes, and only 43 files needed to be read. So now you can see that with liquid clustering, Spark needed to do a lot less work to retrieve the exact same amount of data. And this is where the problem lies with partitioning. You often have to decide on your partitioning logic purely to try and accommodate a more general view on how you want to lay out your data in the underlying data storage. With liquid clustering, you kind of don't need to worry about all of that complexity. You can just say, arrange all of the data in my delta table according to these particular columns, and it will do its best job to try and put that in as few Parquet files as possible, so that when you read or write to that table through like merge commands or whatever that is, you're going to do a lot less work. Now, in this particular example that I set up, I just set up this slide so that I could explain the concept to you, but I wanted to show you the difference in performance from a wall clock perspective. On the partition table, 28 seconds, just short of 28 seconds to do that query for 1 year of data. On the liquid clustered table, just under 7 seconds. All I did was change the same table from a partition table to a liquid clustered table. It literally is a few pieces of additional commands you have to put on the delta table create. And I got all of that benefit 4 times just on this particular example. But as Databricks quoted me in the article that was released about liquid clustering, we actually saw up to 10 times performance improvement by moving partition tables to liquid clustering. And to be honest with you, it is the easiest thing that you can make a change on your delta tables to get a really good bang for your buck if you're working with streaming data. All right, so the third goal that I want to talk about is how do we ingest from a diverse range of data sources? Like I've said, not all data sources that you read in a streaming scenario actually are coming on the typical brokers that Spark is very comfortable with processing. Hopefully they are, but in an industry like Shell's, they aren't. We have very old technology estate that does do streaming, and we do have to cater for a whole wide array of different options of how people that help us run our assets provide us with the information about those assets. And that's not a simple problem to solve. You can often get caught up if you're a Python Spark developer. You're probably doing things like writing all of your ingestion in native Python and then doing a Python pandas data frame to Spark data frame conversion and then writing it from there. You just get into this world of mess, and it feels very hacky. And you kind of wish that you could just write your own. Now, Spark has supported being able to write custom data sources that you want to build yourself in Scala. And that's how you get the jars that you probably are installing for certain streaming data sources. They are written in Scala. But if you like Shell, we don't have many Scala developers around, but we have tons of Python developers around. And so what we wanted to do was really try and change the way that this was working. So we actually reached out to the Spark community and said, we would love it if you could write the API for us to be able to write data sources in Python instead of Scala. And weirdly, they called us up and said, hey, we're doing it. So it was really fun to see that they were listening to us and that they were very keen on building this. So what we have today in Spark 4.0 is Python custom data sources. This was released in Databricks a little while ago. I think it was in 15.4. But the official version that is open source, that you can use in any environment that you want to where you run Spark, can support Python custom data sources. So before Spark 4.0, the typical built-in sources that were supported were files, Delta, Kafka. But then you could also, if you were using cloud streaming services like Kinesis, GCP PubSub, or if you had Pulsar running, you could go and download jars that are written by those particular providers that you could install on your clusters that would give you the option to actually ingest data from those sources. And often, well, the way that you would do it is when you wrote a streaming job, you would say spark.readstream.format, and then you'd choose the format that you wanted to use. Now, just remember that format bit in your mind for now, because this is where the trick comes. And then after that is options, and options allowed you to specify exactly what criteria you needed to use with that particular connector, so what your Kafka Bootstrap servers were, which topic you needed to subscribe to, just all of the different options. And so this is the standard way that you did it before Spark 4.0. You still can do it in Spark 4.0. But like I said, you were definitely limited by the options that were available. With PySpark custom data sources, we are now able to write in native Python our own functions that support batch reading, batch writing, stream reading, and stream writing. So the full capability is supported. This makes it really cool. So if we're talking about streaming data, so you're probably more excited about the fact that it supports read stream and write stream. So you can read from custom data connectors, and you can write to custom data connectors, parallelized, at scale, in exactly the same way that you do any other connector. But you can also do it with batch. So how do we do that? In Spark 4.0, there are some new classes that you can import. So if you go to the py.sql.data source, there's a new class called import data source and data source reader. And you can just now all you have to do is implement the data source class and define a few things for it. So in this particular example, we're looking at the weather API. We're going to build a connector that ingests data from some weather API. This is all generic. This is just boilerplate. If you ran this, it probably wouldn't work. So I'm just trying to use this to explain the situation. But there's a really great documentation on this. So we're going to create a class called weather API data source, and it's going to implement the data source class. We're now going to give it a name. So you know when I said spark.readstream.format, we put in a string piece there that defines what is the format that we're going to read from. And this is where we can say what that format should be. So when we use this, and you'll see this in the next slide, weather API is going to be the name of the format that we will use. We also got to define the schema. So we've got to tell Spark, what is the Spark data frame schema going to be that it returns? And here you can define it as it is. And then we've got a method called reader. And in there, we need to implement a class called weather API data source reader that we give it the schema that it needs to return, as well as all of the options that the user would have put in their code to help us configure that particular connector better. So now you can actually see when you look at this, and if you've written Spark streaming code before, this all starts to look familiar, doesn't it? And now you can do it yourself. And you can do it in Python. So if you've done this in Scala, you're obviously very hardcore and been around since the beginning of Spark. But for those of us who are more into Python, this is really exciting news. Now, how do I use that particular custom data source? So all I have to do now, once I'm in my PySpark code, is I just have to do spark.datasource.register and register that class that I've built. From then on, in my code, I can then use spark.read.format, weather API, and I've got my connector up and running in that particular job. So it's really simple. At Shell, we have done a lot to adopt this. We have built our own connectors for our own industry. I don't think it's going to be kind of familiar with all of you, but if you are into industrial processes, we have built one for Osisoft Pi. We have built one for OPC UA. And we have been building them for different SCADA systems that we use. And the reason why I can do this talk today is because we actually started doing this a year ago when the first release candidates of Spark 4.0 and Delta 4.0 came out. And we've been really trying to push them to their limits because we also wanted to give the Spark community more information about how did this work, how useful was it, how simple was it for a Python developer to get this stood up, but also what was the performance like. And we're really achieving results with the scale of this that matches anything else we've built before. The best part about it that I find is, as a developer, often we need to do ingestion of data at scale. And when we just use native Python, there are ways to do this, but to be able to distribute a workload across your cluster and hit an API in parallel, if it doesn't have too many throttling limits, is not a simple thing to achieve. But with the framework that we've got here with Python custom data sources, it's obviously robust, it's designed for scale, it's designed for parallel compute. But also, hopefully you agree with me that Spark structured streaming is probably one of the most reliable frameworks for streaming data out there. And so you get all of that, plus you can inject your own capability to use it. And so that's really exciting. So let's then just bring it all together. So what does the Spark time series platform look like? Some of you are probably Databricks customers, so what I'm about to show you, you're probably going to go, this guy's mad. I'm trying to, this next slide is, I'm kind of like worried about it because I'm sure there's architects that are going to come and tear me apart after this. But I wanted to just show you like what are the options on the table now with all of this new functionality that has been released. So if you are an open source Apache Spark user, this hopefully makes some sense. We've got on the left-hand side different data sources that we can ingest from, SDKs, APIs, OPC UA. We can now use PySpark custom data sources to read from all of these data sources natively into a Spark data frame without any of the hoops that we've had to jump through before. We can have Apache Spark running on your on-premise Kubernetes cluster or your on-premise compute, whatever it is that you're doing. And it is now taking those payloads it's receiving from these different data sources, and it's using the variant type to store it in a simplified data model in your Delta Lake. Your orchestration engine, if you are running open source, is likely going to be something like Airflow or Dagster or Prefect or something along those lines, maybe your own thing. And that orchestration engine can now execute Python code to your Spark clusters using something called Spark Connect. I didn't have the time to unfortunately talk about Spark Connect. Hopefully you're going to hear a little bit more about it in the summit this week. It's probably one of the best things that have come out with Spark 4.0 as well. But it allows you with a client-server architecture to basically connect to your Spark clusters much simpler than ever before using Python. So once you've got your orchestration that is running your streaming job, it can also you can also connect it to Databricks. So Spark Connect also can connect to clusters set up in Databricks. And it's all writing its data into Delta Lake. Unfortunately, the text at the bottom of the slide is hiding that Delta Lake, if you've set it up with liquid clustering, is obviously adopting all of those benefits. Now, all of this is available in the native Apache Spark and Delta Spark open source versions. And it provides a lot of capability for you to really be able to process time series and streaming data better than ever before. One of the things that you're probably still wondering, when I started this off, was talk about what are we doing about being able to match time series database capabilities in Spark? Like, how do I do resampling? How do I do interpolation? And that's a very good question. And so at Shell, we have an option, and I would say there's two options that I'd be happy to put my name behind. The one is that in Databricks Labs have a package called Tempo. And Tempo is a really good package. It's downloaded millions of times. It's very popular. That allows you to do time series queries in PySpark. So you can download it and install it. The other one, which is available here, is an open source package that is available through the Linux Foundation. It's the Energy project. I'm from Shell, so that's where we open sourced it. The RTDIP is open source. We're very proud of it. But it also provides you with a rich set of functions that you can use to query time series data. So you get all of your queries that are like resampling, interpolation, time-weighted averages, which I can tell you is not a simple thing to write, circular averages, interpolation of time, a number of different queries. But what we did was we didn't want to only allow this package to run in Python. We wanted to support SQL as well. And so this package comes as a PyPy package. You can install it. You can use it in your PySpark jobs. But you can also just install it in your own Python notebooks outside of Spark. And if you're using Databricks SQL, you can configure it to just read the data through Databricks SQL and perform all of these queries for you and return it in a pandas data frame. So please check it out. There is a lot of us that are working on it. It's gone a long way. We are not going to be stopping anytime soon pushing behind this. This is one of the best things that we've done in the open source world from Shell, and hopefully we'll get some of you to use it as well. So with that, I'd like to say thank you very much for attending the session today. It's great to see an audience. Hopefully I've given you some insights as to what are the best things that are coming out in Apache Spark 4.0 and Delta 4.0.